Yeah. So what I'm going to talk about is how by tuning the nature of noise statistics across heat baths, we were able to tune the performance of a micro heat engine that we made with this single colloid. Now, before I go to micro heat engines, let's quickly recall what the macroscopic heat engines are. So these are basically machines that take some amount of heat from a hot reservoir at a temperature TH. On the virtue of it, it performs some work and gives away some heat to a cold reservoir at temperature TC. Now, the energy balance of this process is given by the first law of thermodynamics, while the limits of this energy conversion is given by Carnot. So he says, like, if you perform a cyclic process with this engine in a reversible manner, where you have this two isotherms connected by two adiabats, you have the maximum efficiency for this energy conversion, which is given by 1 minus Tc over Th. Now, these adiabatic processes are hard to realize, and more of a practical protocol is the Stirling cycle, where you have this adiabats replaced by these isochoric processes, where you don't change the volume of the system, but change the temperature and hence the pressure. So in this case, the work is given by the temperature difference and the volume ratio. And even in the quasi-static limit, the efficiency is going to be lesser than the Carnot one, because these isochoric processes involve heat exchange with the surroundings and don't contribute to any work. Okay. So now these conventional engines have this working fluid which has Avogadro number of particles and hence so many degrees of freedom. And the question is, what if the degrees of freedom are a few? Can we perform an engine? And the answer is yes. So in that case, the working fluid of the engine is replaced by the single colloidal particle which is dispersed in a thermal fluid. And the valves of this dashpot and the piston is replaced by this single harmonic potential, which is usually created by focusing a laser into it. Now, the pressure is just the position of the particle and volume is the stiffness of the potential. Now, using this concept in this seminal experimental work, a Stirling cycle, as I showed you earlier, was performed using the single colloid. So now the thing to notice is that the distribution of particles' position in equilibrium is a Gaussian, and the width of it is decided by the stiffness of the potential and the temperature according to equipartition. Now, the isothermal processes in this case are the ones where the temperature of the water bath is kept constant and the stiffness is varied, and the isochoric processes are the ones where the stiffness of the harmonic potential is kept constant and the temperature is varied. Now, without going into further mathematical details of how one can calculate the thermodynamic quantities out of a single fluctuating trajectory, I can tell you that the thermodynamic quantities are not going to be constant across cycles, since there is only 1 degree of freedom, and the fluctuations are going to be comparable to the mean. So in this plot, I'm plotting the work. So in this, I'm plotting the work per cycle as a function of cycle number for both the forward and the reverse direction of the cycle. So you can see for both of these, the work per cycle is fluctuating below and above zero with this sort of a distribution. But if you consider on an average, you see for the forward direction of the cycle, it has a negative, finite negative mean value, which means that it is on an average acting as a heat engine, whereas for the reverse direction, it is acting as a heat pump. Now, if you were to plot, okay, so now if you plot the average of these work distributions as a function of cycle duration tau, you see that the average work is highest in magnitude at the highest cycle duration. And as the cycle duration is reduced, the magnitude falls monotonically. Now, why this happens? This happens due to the buildup of irreversibility during the isothermal expansion process. So in the beginning, when the harmonic potential is stiff, the probability distribution is narrow. And when the harmonic potential is stiffness is reduced rapidly, it still takes some finite amount of time for the particle to explode the available phase space. And when work is calculated like this x square, this is not proportional to the stiffness anymore, and hence the work magnitude falls. Now, the similar sort of irreversibility was predicted by Curzon and Albon for all sorts of macroscopic engines, and because of which the power which is given by work by cycle time is bound to go through a maximum as the cycle duration is decreased. Now, the same thing happens for these microscopic heat engines, and therefore, on an average, when operated between thermal baths, they perform like their macroscopic counterparts. Now, the question is, what if the bath themselves are out of equilibrium, like the active baths? So there is no macroscale equivalent for this, and we know that the natural micromachines such as molecular motors and so on work in similar environments where the noise is much more complex than just a thermal bath. It has non-Gaussian statistics and long correlation times. So first attempt to solve this problem was to throw bacteria into the solution where the colloid is and perform the same Stirling cycle quasi-statically with the single colloid. Now you can see, because due to the presence of this bacteria, there are these huge tails, non-Gaussian tails that has come up in the probability distribution of particles position. And as a result, the work done per cycle, which is given by the area under this plot in the PV diagram, is 2 orders of magnitude higher than an engine which is working between 2 thermal reservoirs with the same temperature difference. This is the area for the thermal one. And of course, if you see the efficiency, you see that the efficiency for these active engines for many temperature differences are much higher than the thermal ones. And for certain temperature difference, it exceeds the Stirling saturation efficiency. So this is just the distribution of position of the particle. So therefore, of course, the non-Gaussian fluctuations here are driving this active engine to outperform the passive ones. But this is only happening in the quasi-static limit, meaning because the finite cycle durations where the irreversibility occurs, it was inaccessible in the experiments with live bacteria. And also, as pointed out by this paper, that in this sort of active baths, there is this effect of noise, non-Gaussian noise statistics and finite persistence time, which could not be decoupled in these experiments. Now the question is, what happens in the finite cycle duration, and how one could see the separate effects of noise statistics and persistence in these complex environments. Now to address that, we did reservoir engineering. So in reservoir engineering, what we do is, like, imagine this is the colloidal particle, and this red spot is the focal spot of the principal laser, which is creating the harmonic potential and confining it. And now there is a secondary laser, as shown in this diagram, which is reflecting off a spatial light modulator, where any desired phase pattern can be put into it. And we put this sort of a blaze grating phase pattern to flash the secondary laser spot at different distance, different positions. So we flash them along this line at different time instances, and the force that it imparts to the particle is proportional to the distance delta A that it is flashed from the center. Now, if you choose the delta S from this sort of a distribution, which is a Gaussian, you recover a resultant Gaussian of the particle's probability distribution. And of course, the effective temperature is going to be much higher in this case, since extra noise is being given. Now, instead, if you choose the delta S from this sort of a distribution, which is a short noise-like distribution, you recover a non-Gaussian distribution of the particle's position. Now, which is very similar to the ones in the bacterial reservoirs. Now, the advantage of this is, due to this short noise, no further correlation is added to the particle, and hence we can study purely the effects of non-Gaussian statistics. So to study this, so what we did is we performed this non-Gaussian Stirling cycle. So this is exactly the same protocol as before, except that across the baths, when you perform these isochoric transitions, not just the temperature changes, but also the statistics of the reservoir noise. So for the hot reservoir, you can see there are these non-Gaussian tails, and for the cold reservoir, it's a Gaussian one. So when we perform this cycle, so we also performed an identical Gaussian engine where both the reservoirs are Gaussian, and I'm just plotting for you the work as a function of cycle number for that. And you can see these are this is a typical work fluctuation, and when I plot the distribution of work per cycle as for different cycle times, I see that all these work distributions are Gaussian. And as you go down in cycle duration, just the distribution spreads up. While for the non-Gaussian engine, this is the typical work fluctuations, and you can see that they are highly non-Gaussian. And when I plot the distribution for different taus or the cycle durations, you can see that it fits to a Gaussian only for the highest cycle duration, which is at the quasi-static limit. And as we decrease the cycle duration tau, it develops a negative tail. It develops a negative tail. So to quantify this distribution, we looked at both the most probable or the mode of this distribution and also the average of this distribution. So here in this plot, I am plotting for you both these quantities for both the Gaussian and the non-Gaussian engine as a function of cycle time. So you can see for the Gaussian engine, both the average and the most probable, they remain flat at all cycle times close to the Stirling saturation work. Now this means that due to the fast driving which has occurred at the small cycle times, there is no further irreversibility is added to the system. But for the non-Gaussian engine, you can see, although the average work stays flat at the Stirling saturation work, the most probable one, however, it decreases in magnitude and crosses 0 below tau equals to 10 seconds. This decrease in the magnitude of the most probable work must be associated with the irreversibility. And this irreversibility is due entirely to the non-Gaussian statistics. And as predicted by Curzon-Albon, the work per cycle as a function of cycle time can be written like this, where this W, this is the dissipative work, and this is the irreversibility parameter, and we find that this irreversibility parameter is actually dependent on the statistics of the reservoir. Now, in this plot, I'm going to plot the power as a function of cycle time. So the most probable power is just work per cycle over the time. And you can see that as a result, this power goes to a maximum and then falls down below 0, below tau equals to 10 seconds. And this was done with the kurtosis or the tailness of the probability distribution of particles position being 20 in the hot reservoir. And we changed the tailness of the particles probability distribution in the hot reservoir and performed another engine, and we saw that this peak of the power is shifted across the cycle duration. You can see that this plot crosses 0 below tau equals to 6 seconds, and this plot crosses 0 below tau equals to 10 seconds. Therefore, and of course, we fit it according to the Curzon-Albon profile, and we see an excellent agreement. And when we calculate the efficiencies, we see at the maximum power, like here and here, where the power is maximum, we find that they agree pretty well with the theoretically calculated Curzon-Albon efficiency for the thermal engines. So therefore, just by tuning the statistics of the noise, we can modulate the mode of maximum power production of this engine without altering the efficiency. Thank you.
Yeah, great talk. So two quick questions. So yes, you said you get these tails in your histogram. Is that because, so even if you take the bacterial suspension that you have,
right?
So the bacterial suspensions, basically they're random kicks to your colloidal particle, right?
Sorry, I couldn't hear.
Okay. The bacteria,
yeah,
they're basically kicking your colloidal particle in a random fashion.
Right.
So is that the reason why you're actually seeing the tails in your histogram? Is that because of the randomness?
Yeah, it is random, but it's not very uniform in time. Means it occurs once in a while. Like the time scale at which the colloid is fluctuating due to the thermal noise, that is much faster. While this kicks due to the bacteria, which might be coming due to the swirls they generate or they physically hit the particle, they happen once in a while. Like, for instance, in a second, there might be only some 3 or 4 kicks. So these are essentially rare events that occur to the particle, and hence you find those long tails. And in our reservoir engineering technique, we are providing it artificially through this secondary laser trap.
Just one more.
Yeah.
you said that when you have a non-Gaussian signal being fed,
Yes.
and you said there's no further correlation which is added.
Right.
Correlation with what? What is
correlation? The autocorrelation of the particle's trajectory is not increasing as a result of that. So I didn't show those plots which will prove that, but yeah.
Yeah, this is further on the question of noise statistics.
Yes.
You know, supposing you took a particle and put it in a evacuated, not completely evacuated, but low pressure chamber.
Right.
At the level of pressure, so you maintain it with a pakka thermostat. Okay?
Right.
So it's at thermal equilibrium.
Yes.
But the kicks are occasional.
Right.
That is still a thermal equilibrium system. So it cannot be the mere fact of occasional kicks that makes your bath non-equilibrium.
Right.
Non-equilibrium. If you think of a colloid being kicked around by molecular collisions,
right,
the molecules have a velocity drawn from thermal distribution. So
yes,
the impulses are roughly drawn from that kind of a distribution.
Yes.
The fact that it's Gaussian has to do with the central limit theorem, adding a large number of independent things which whose variance exists. So
yes,
somehow your explanation that the occasional character of the kicks is what makes it non-equilibrium can't be quite right? It must be either the fat tails or correlations or something else.
Right.
Yeah.
So for the bacterial reservoir, the reason that it's non-equilibrium is the long correlation in the particle's trajectory that also come about. But
the particle's trajectory is an outcome.
Yes.
It's not a path property. It's an outcome of, So the question is, what property of the bacterial bath really makes it non-equilibrium?
So there are these flows in the system, right, which is generated by the bacteria due to the consumption of energy constantly.
Yeah, but somehow I wasn't satisfied with the explanation you gave to the earlier question. I have a feeling it must be that the kinds of kicks, the individual kicks the particle gets, even when added up in a large number, don't give you something like the noise in a Langevin equation. The tails are too big, or something else must be at work.
Right.
Also, it's unobvious what all of this has to do with the deep property of non-equilibriumness, which is the lack of time reversal invariance. So where does that come in?
Yes. So for the bacterial reservoir, there must be all these properties that of the equilibrium that must be being violated. But for the reservoir that we engineered, so when we looked at the particles correlation and all of that, it didn't change as compared to the thermal reservoir, and we could actually equate the diffusivity of the particle to the the width of the probability distribution in the trap and all of that, and we could calculate an effective temperature for our particles. So in that way, our reservoir was not very similar to the reservoir with the bacteria, except the statistics.
Okay, I'll bug you more later.
Yeah, sure. Thanks.
So hi, I wanted to ask that you are giving a secondary laser,
yes,
to drive that particle, like what you have shown in for active particles. So I wanted to ask that the distribution you showed, it's a non-Gaussian distribution. It's not symmetric in both sides.
Right.
What is the reason?
Yeah. So actually those the tails that come about, those are really hard to control. We need like a lot of statistics. The data that I showed here is not really for a long time, so hence there is some slight amount of skewness in that. But we did like many experiments with them, and if you had calculated the skewness for all those distribution for different experiments, the average will be 0.
So there is 2 laser point only, or you showed 3 in the not?
No. So there's the secondary laser that is flashed at different time instances.
Yeah.
So there is only one secondary laser spot, which is flickering essentially. Yeah.
Just a quick question.
Yeah.
Nice talk. Have you looked at the if there is any effect of skewness of the distribution, because you looked at the kurtosis?
Yes. Yes. So I have checked that of course the probability distribution of the work also gets skewed, but I haven't looked at it thoroughly to
So I
check.
meant, like, if you make it deliberately skewed by flashing on the one side more.
Yeah. So we didn't check it by deliberately skewing the distribution of the flashing traps, but whenever there is a skew, we see the work distributions are deviation from the Gaussian and all of that.
So we'll try to take as many questions as possible, I think. It'll spill into the coffee break, but I hope it's okay with all of you. Okay. Yes, there's one more there and then another one.
So, hi. So, in some slide you have showed for the active bath,
Yes.
in the efficiency, there is some term Kmax and Kmin.
Right.
So does it have some thing to do with the non-reciprocity or whatever you were showing the efficiency? The Kmax and Kmin time, can you show that?
I will just maybe go to that slide. Is this the one you are talking about?
Yes, this one.
Yeah. So what was the question again?
So the question is that what is this Kmax and Kmin, and if it has some relation with the non-equilibrium thing or your non-reciprocity, whatever you are getting some non-Gaussian thing.
Right.
Yeah.
So actually it turns out that so basically this Kmin and Kmax are the maximum and minimum stiffness of the harmonic potential across the cycles.
Yeah.
And actually it turns out that the equipartition that I showed earlier, it is not followed when you have these long correlations in the particle's trajectory. So what happens is that this equation.
So I mean, does it have something to do with the how much frequency the bacteria are kicking the particle? Means that in some, if you say some thermal bath, then the relaxation time or how much frequency they are getting this,
Yes.
like that.
Yes.
And this is not actually not equal, means this does not have any distribution Kmax Kmin in your equilibrium case. So does it have something to do the non-reciprocity thing?
So I didn't understand what you meant by.
So so I'm intending that if we think it has a two reservoir, and the Kmax and Kmin, these are different for your active case, which will not be for your equilibrium case. So does this Kmax Kmin thing is differentiating from the equilibrium case?
Okay. Yeah. So basically, so according to this equation, when you have two different cases, the width of these probability distributions will scale accordingly. But when you have it in the bacterial reservoir, it doesn't quite scale accordingly. The stiffness values itself are dependent on what is the correlation that is present in the system, this exponential. So the Kmin and Kmax, what appears in this case is slightly elusive to calculate according to the just by looking at the distribution for a finite time.
I think we'll move on to the next talk.